Thank you, Alessia, and hello, everybody. A very warm welcome to all of you, and of course, a very warm welcome to this fantastic panel. I'm very much delighted to be the moderator of this panel. Let's kick it off, and let's think about, for a moment, someone would come to you and tell you, look, there is a $1.4 trillion opportunity on the table. Would you buy into this? Would you invest into this? Would you think about doing something about this? And of course you would do this. The 1.4 trillion, this is the economic value which has been elaborated, researched by our McKinsey Global Institute, by our teams with a focus on quantum computing. And this is the opportunity as it looks like currently. And the panel today is about quantum in operations. So basically, we will discuss how real is this opportunity. And we will start with the first question about, what is basically the position in the quantum ecosystem? So, Daniela, let's start with you. What is the position of Deutsche Bahn in the quantum ecosystem?
Yeah, for Deutsche Bahn, it's clear we will be a consumer or customer of this technology, and we have a clear mission to say we want to be first mover and not first fast follower. And that is why already in 2019, so almost like 5 years ago, we started to set up our own quantum team consisting of crypto experts, software engineers, quantum experts and physicists to really observe what's going on in the market with this emerging technology and to develop for Deutsche Bahn use cases where we can benefit from. So we did first trials with quantum annealing and with this hybrid mode of high-performance computing and quantum computing, but we cannot do all ourselves. So for us, it's really important to have an extensive exchange with industrial partners and research partners to get a good overview what's going on. And you might ask, why is Deutsche Bahn interested in that topic? And you might say it's a disruptive technology, like the winner takes it all, or at least the winner takes most. But that is not the key point for us. For us, it's important not to be surprised and to be prepared when it's coming to that breakthrough. Because when we look back at artificial intelligence and ChatGPT, everyone was kind of surprised, and I said, hey, I don't want to be surprised, I want to be prepared. And therefore, for Deutsche Bahn and me, it's not to fuel the hype about quantum computing, but it's really like to have a close ear on the rail to understand what's going on.
So breakthrough and technological disruption, I think, are two keywords here. And, on the bottom of the stack in the quantum tech ecosystem, the hardware is important. So with IQM, I think we have the European lighthouse represented here on the table. So Jan, talk a little bit about IQM and how you look into the ecosystem.
Yeah, sure. And maybe before I go there, you mentioned AI, and many people here mention AI, which is maybe now coming in operations. And the question is, why now? Why not earlier? Because these concepts in AI, they have been out there for decades already. And the reason is that we are now ready from a computational power point of view. So the hardware actually became ready to, for example, train these large language models or do other things. And we are in a similar situation with quantum as AI was before. So the concepts are there. We know how it could be done. We know algorithms. We know concepts like error correction, but the hardware is not there. And this is kind of our task in the ecosystem, is we kind of provide the engine, basically the computing power. So we see ourselves as a system provider based on superconducting technology, which is one of the most widely used ones for it. And we are building full systems and also deploying them. At the moment, not so much yet to customers like Deutsche Bahn, but more to scientific and research institutions, which are very interested to use these computers already today to solve scientific problems, but also to educate the workforce, another very important topic. And basically, we bring out a new processor generation, let's say, every year. And at some point, there will also be this AI moment, let's say, for quantum, where the computing power is sufficient to run your problems or any other problems that the industry might have. And this is kind of our task as IQM in the ecosystem.
Excellent. So we will come later to and talk a little bit about the challenges and how far you are in the development of the hardware. But before we do this, we have another lighthouse represented here, a bit upper on top of the stack, focusing on software with Markus representing Terra Quantum. So Markus, your perspective on that ecosystem.
Yeah, I think it's a great representation, actually, the hardware stack, the end user, and kind of the software layer. Indeed, Terra Quantum focuses on the application layer. There is, in the moment, of course, a lot of the attention in the ecosystem on the hardware, make these chips scalable so that you can use them beyond toy problems. But ultimately, I think it's in quantum not different than in the traditional IT industry. Software rules the world, so to say. As soon as we have the hardware problem solved, the attention will shift to the application landscape. Where are the use cases? Where's the software to run it and create business performance? That's what Terra Quantum is doing. So we have built a large library of quantum algorithms for 150 plus use cases in various industries, including mobility solutions, route planning, and stuff like this. The important thing, I think, is that we bring this into operation already today. I think the industry is kind of, a little bit bored now by doing toy problem stuff and studies. We have to come to corporates like Deutsche Bahn and present a solution where we can enhance business performance today. This in a pure play quantum mode, quantum algorithms on a pure native QPU isn't yet possible. We are not yet there in terms of the quantum utility, the quantum advantage. But what we can do is hybridize the problem. So work with simulated hardware, simulated qubits on a classical HPC to deploy the quantum software, which we can write today, already today. And by doing so, I think there is great work done across the globe now to showcase and underpin that we can create outperformance vis-à-vis the best-in-class classical implementations when we do this hybrid approach and when we select the use cases wisely. So therefore, that's our approach. Early commercialization, hybridize the problem, do quantum and HPC kind of together. And by doing so, we have a lot of use cases where we can unlock business performance today already.
I think use case is a great keyword. Let's ask the user. What is, in your perspective, the potential of quantum? We are talking about quantum in operations, and I think especially for a company like Deutsche Bahn with a focus on transport and infrastructure, it must be an incredible potential perceived or seen in that technology. So what's your perspective on that?
Yeah, for me, there are two types of use cases. The one is really with a big potential, as you mentioned, and the big opportunities. But on the other hand side, there are big threats, talking about cybersecurity. As an optimist, let's start with the potential. And I brought you a little graphic. And most of you might know that because this is a real problem that we in the German railway system have to solve. The traveling salesman problem, for the ones who don't know it. So you have to find an optimized route to go from place to place and come back to the place where you started from. And when we start nice and easy, it's about 5 cities. There are 12 possible roads, and a computer can find the optimal route in 12 nanoseconds. Easy. So next step is let's go with 20 cities. There we have already 60 trillion possibilities, and the computer needs 2 hours to find the optimized route. And you can imagine that our dispatchers, so our employees who should oversee the whole traffic system, cannot really find this optimized route anymore. And we talk about 20 cities. Now let's face reality. We at Deutsche Bahn are talking about, where do we see that? Here, 5,400 train stations that we have to pick. And next one, just a moment. So now we see it. And you can see with 235 are with ICE access, so our high-speed trains. And we have 425 ICE trains by 2030. And we run 50,000 train rides per day. And currently, that's not possible for any conventional computer to solve this problem, but we hope that quantum computing makes it happen, because I'm actually not only dreaming, I'm striving for a real-time schedule or real-time timetable for our customers. It will have a huge impact with any kind of disturbances, like in seconds instead of years, we can find the next best route for the whole optimized traffic system. And also, and that is important as well, with software we can put more trains on the same infrastructure. So from our perspective, there's really huge potential. But on the other hand side, if I may say another use case, like cybersecurity, it's really something, and Deutsche Bahn is part of the critical infrastructure. If quantum computing is there, then all our cybersecurity algorithms will be breakable. And so how do we handle that? And that is important to be prepared for that. And that is why in our team, we work with crypto experts and really say, how do we come for the post-quantum era, how it's called, really create for crypto and quantum agility, so that we now already focusing and testing how we can harden our algorithms on a cryptography point of view to see that we are safe and secure when quantum computing all of a sudden might break in.
So Markus, listening to the users' requirements, you as an expert on the software side, working already with clients on those topics, how close do you get, based on your simulation, to quantum advantage?
Yeah, I mean, quantum advantage, of course, is, let's say, in a way fuzzy, because we will, advance the hardware in a way that there is a continuous kind of exponential curve in the growing compute power. So where are we at that curve, right? With hybrid techniques, and I want to kind of present probably 2-3 use cases out of other industries where we see already where we are today with those hybrid techniques. So to begin with, we work with Thales, the European Aerospace Corporation, and we looked at optimizing their satellite mission planning. So the Earth observation satellites cross the Earth, and their task is, they are commercial satellites, to maximize revenue while they cross the Earth. And they get a lot of picture requests, and they have to prioritize those which maximize the revenue. It's a very, very complex optimization algorithm. So we moved that into the quantum space, created a quantum algorithm for it, and deploy it on those hybrid techniques. And with this, we could improve their task completion rate to almost 99%. That translates into, if we consolidate it across the whole global fast-growing Earth observation satellite market, to a few $1 billion in additional revenue potential. That can be captured today. One example. Another one also with route planning is we work...
Do you see a real, let's say, impact already compared to working with high-performance computers?
Oh yeah. I mean, this outperformance, which is, per 2 satellites, it's close to 20 million or so. This additional revenue potential you can get today, and you will not get it just with tuning your classical algos. You need the quantum ingredients of the software here. Same with, we worked for Honda Research Institute, and looked at the disaster evacuation routing. Yeah, and were able to improve the accuracy of those escape routes by 7%. This again translates into substantial less time to escape from an emergency site. This is again, this is possible with hybrid techniques. One last example, but to give you a crossover of the industries which are affected. For the financial services industry, we work for a London-based hedge fund, and they do, beyond other things, they price exotic options. It's a very critical thing for your risk scenarios. And we were able that, we by time reduce the time needed by 75% to price those exotic options. It's a substantial risk advantage, competitive advantage in the industry. Again, all of that can be realized today. The potential will grow as we grow and mature the hardware, but we can already unlock substantial business performance today.
Yeah, so I think that's a great segue to the discussion about the hardware, because everything what you were discussing is based on quantum simulation. Yeah? So basically you are simulating on high performance computing infrastructure what might be possible. Yeah? So what is possible already when you look into the hardware development?
So the quantum computers that you find out there today, you can run algorithms on them, but the thing is that these processors and these qubits, which are the computational elements, they make errors. So this means the algorithms that you can run, they're not of indefinite length. They're actually quite short. And this limits you in the problem size, for example, that you can tackle. And one always has to be careful, because if you read the news, for example, often you read this company has so and so many qubits, this company had this many qubits, but actually it doesn't help you if you have many qubits, but you can only run a very short algorithm. You will not gain anything. Also, it doesn't help you if you have, let's say, only 2 qubits and run a very long algorithm, because this can still be simulated by a laptop computer. So in the state where we currently are, where you have these errors, so you have no error correction, basically you want to scale the number of qubits and the quality, so the length of the algorithm at the same time, and this is hard to capture for a non-expert, let's say. And the question is if at all there are use cases of commercial relevance in this non-error corrected time. I'm a strong believer of it, and what you can do today to answer the question is basically do quantum physics, so simulation of quantum physics, and this is why we start at the universities, scientific computing centers. They are interested in these problems today, and it might evolve into simulating some kind of chemistry phenomena, maybe even into the bio sector of pharmaceuticals, where you simulate quantum systems with these non-error corrected qubits. And then Markus was talking about this exponential curve. I would say there are 2 of those. One for these non-corrected computers, but then of course there is this paradigm of correcting the errors. And this has its own exponential curve, but you have an overhead. You need maybe 1,000 or, depending on you do it, 100 of physical qubits on your processor to implement one computational element. And there we are still quite far away from to have a large-scale machine of this type. But with the other ones that we currently have, for sure, you can do already quite a lot of interesting physics. And if you think about computing again, this is also how it started there. These computers, the early ones with the vacuum tubes, they have been set up in universities, and people have been doing scientific experiments with them in the first place, and we see where we are today. So I don't think it's a bad thing. It just means that we need to take the time, we need to be patient to make sure we actually have the long breath to go all the way to the end.
So as you are focusing on superconducting technology, you are competing with large giants like IBM. They have announced the next 1,000 qubit chip coming soon. So what are you different to compete against those giants and be successful in that competition?
So first of all, again, people should not look at the qubit numbers. I think that's the wrong metric. But in the end, what we do is we are kind of a chip industry. So if you look at a company like Intel, they bring out a new processor every other year or so, and that's the same for us. And then the question is often, who will be the winner? But there is no winner in semiconductor industry. Moore's law has been going on for whatever, 50 years. It's a race, and you just want to stay on top of the race. So the question is, can you stay one of the leading companies? And there I'm actually very optimistic, because it's about innovation. And innovation is, in the end, down to people, the best ideas, the best research. And this is something that here in Europe, actually, we're very good at. If we consolidate our efforts, if we bring the kind of financial firepower to the table. And this is what we have been doing so far quite successfully. And I'm very optimistic that also in the future we will be able to keep up with the big giants out there.
So as we are getting close to the end of this panel discussion, let's discuss a little bit about what do you expect for the upcoming next 2-3 years in terms of announcements. Yeah, if you look into the latest announcements, Qurera announced 48 logical qubits. PsiQuantum is still telling everybody that a fault-tolerant computer will be available in 2026 latest. So let's put a little bit reality into all the vision we have in mind. What real announcements do you expect over the next 2 years? Maybe Markus, start with you.
Yeah, I think what we'll see is, and I think this is very important, regardless of the, how those quantum hardware matures, what we see is that two waves which we were seen as being distinct waves, the AI wave and the quantum wave, I think they merge together. We, for instance, have a partnership with NVIDIA, AI chip producer, world market leader. The hybridization and to use quantum and quantum software to enhance classical Gen AI tools, e.g. next iteration of the LLMs, large language models, you have to compress them, otherwise the inflation of the parameters, you can't deal with classical infrastructure. So I think that what we will see, 2024, will be the year where QAI, adopting Gen AI application and enhance them with quantum techniques will happen.
Daniela? What do you expect?
You ask me,
what do you wish?
Wish is a different topic. What do I foresee in the next 2 years? And forgive me for that. I don't think there will be major announcements in the next 2 years, but that's not the important point. The important point for me is that we fight our European position in this global game. And I think from the investments that we currently see, so when we think 15 billion of quantum investments in China, 4 in the US, but 8 in Europe, is quite a good position investing in quantum computing. But now it's the question how we scale that business, because we had it already in Europe that there were great innovation by great minds, but how do we make money out of that? And to be prepared for that magic moment, that is something where we really have to share, network, do best practices to keep this disrupting technology here in Europe. That would be my take. And so it doesn't matter if it's 1, 2, or 4 years, let's go for it and be prepared.
Jan, as you are European lighthouse, final last words. Do you see the fault-tolerant computer coming over the next 2 years, or 4 years, or 10 years?
Well, 2 and 4 years might be a bit optimistic. 10 years sounds more reasonable. And I think the most important thing is what I said, is that we stay patient, also on the capital side. So you talked about funding, and people sometimes now talk about a quantum winter, so a decline in funding. I don't think this is specific to quantum. The numbers have been declining last year, but this is an overall trend. But what makes me optimistic is that people nowadays, or companies, they publish their roadmaps, and they follow the roadmaps. So basically the success is there, and this creates the trust also among the investors. And as long as we keep this, that our promises are such that we deliver on them, I'm actually quite optimistic that we can go even 10 years to a fault-tolerant quantum computer.
So we are at the end of the panel discussion. Thank you very much to this great panelists. Give a big hand. Thank you.